Welcome back to Chapter 35 and Relativity, and we're going to begin today with a thought experiment. So let's just say that there's one car driving this way, and there's one car here driving this way, and somewhere on the sidewalk there is a person just kind of standing there. Now let's say this pedestrian here observes from their perspective, it looks like one car coming toward them this way and one car coming toward them that way, right? However, if we take, for example, the driver of this car, this person's perspective into account, what does it look like from their perspective? It looks like this car is approaching them very quickly, and also this person who's standing there looks like they're approaching their position, right? And of course, the opposite is true. If we're talking about the driver of this vehicle, it looks like this person is approaching very quickly, and this person who is standing on the street is approaching the car, right? That's what it looks like. Those are the perspectives of these three people. We call these perspective frames of reference. In each of these frames of reference, different objects can appear to have different velocities. And this, of course, is because velocities are relative. In 1887, they built this thing called a Michelson interferometer. Now, I've included a diagram in the Chapter 35 page and also in the class files because, well, to be completely honest, my art skills are terrible, right? So let's say we've got a laser here. And here we have a 50-50 beam splitter, right? This thing. So what this does is when the laser hits it, half of the light is going to reflect off of it, and half of it is going to go through it. And now let's say that we got a mirror here and a mirror here. And let's just say for the sake of argument that this length and this path length are exactly the same. And then down here, we have a detector. Right? Now, the light from a laser, if you remember, is collimated. So the light goes here, half of it is going to go through, it's going to hit this mirror, and then half of it is going to go back into the laser, and half of it is going to get reflected down here to the detector. Some of this energy, some of this light that hits this is going to reflect off of it, of course. The other half that doesn't go through. It's going to go up to here to this mirror, and then go back down here to the beam splitter. Half of it is going to reflect and go back to the laser, no problem. And the other half is going to make it down here to the detector. Now, if these two path lengths are identical, then that means the distance that the laser light has traveled, either up the upper path or the lower path, to get to the detector, if these two path lengths are the same, then the light has traveled the same distance to get there. And it should be in phase when it gets to the detector and make a bright spot, right? What we call constructive interference. Now, in 1887, they built one of these so that this axis was like along the equator, because what they expected to see was that there would be a slightly longer path length here as a result of the Earth's rotation, and the pattern that we'd see at the detector would be different, right? We wouldn't see the constructive interference here. But there was no shift due to the Earth's rotation, not even a tiny bit. And this was our first hint that the speed of light is invariant in all frames of reference. And what that means is light is always moving at the same speed, regardless of if you're measuring the light by going toward it or away from it, or if the light source is moving at 50 miles an hour or whatever. If you're in a frame of reference that's moving at 1 mile an hour, at 10 miles an hour, at 100 or 1,000 or 100,000 miles an hour, it doesn't matter. Light will always look like it's going away from you at the speed of light. And so the speed of light, as we say, is invariant in all frames of reference. This, of course, is true because the laws of physics are true everywhere. This gives rise to a very funny phenomenon that we call simultaneity in relativity. Now, I bag on the book a lot, but the example that they use in the book is actually pretty decent. And what they say in the book, what the author says, is that, let's say you've got a spaceship, right, with an open room. There's, I don't know, some wing thingies on it, right, and a thruster or whatever. And inside of it, in the very center, let's say you've got a rectangular type room, right? And let's say you're standing here, and there's a light in the very middle of the room. Now, because you're moving at the same speed of the rocket, right, it's going to look like the light is going to go out in a sphere from there, and the front of the rocket is going to be illuminated the same time that the back of the rocket is, assuming this is directly in the center. Seems pretty straightforward, right? However, let's say you're outside of the ship, and this is moving at a very fast velocity, what we call a relativistic speed, some significant portion or fraction of the speed of light. Now, if you're outside the ship and, you know, somehow able to see inside because this is made out of plexiglass or whatever, right? In the observer's frame of reference down here, or, I don't know, on the ground on a planet or something where the rocket ship is passing by, then the light here is going to be moving this way, right? And the back of the ship, or the light moving toward the front of the ship and the light moving toward the back of the ship, are going to be moving in opposite directions, right? And thus, as time goes on, the back will appear to become illuminated first because it's moving in the same direction as the light, or excuse me, in the same direction as the ship, but in the opposite direction of the light, right? And so while the ship is moving this way, along with the back of the ship, the light is moving towards it. And because this is moving at some significant portion of the speed of light, it's going to look to this observer like the back of the ship illuminates before the front of the ship. Crazy, right? And so we can immediately start to see that this concept of the frame of reference is very important for the study of relativity. Choice of frame of reference gives rise to another funny phenomenon called time dilation. Now, I tried to find a good image for time dilation, but really there aren't a whole lot of them. And so let me just give you a nice familiar example. The one that Einstein used was this idea that if there's like a train moving this way and two lightning bolts strike here and here equidistant from the train, which one are you going to see first? And the idea is that because the train is moving this way, the train should reach the light wave here first, whereas it's going to move away from this one. And I don't think that that's such a great example, because you're talking then about a train that's moving at relativistic speeds really, really fast. And mostly we can't move trains at some significant fraction of the speed of light. So while true, it's going to be hard to test. However, there's another example that we use pretty commonly, also involving a train car. So let's say we got a train car, right? This is now a side view. And you're the observer standing here on this train car. And in the middle, there's like a dividing wall, okay? And then there's like a light bulb or something that'll give off light. And then up here, there's a mirror. And then here on the other side, there's a detector, so that light will get generated here, and it'll go up here to the mirror and come back down to the detector, right? Now, because the speed of light is invariant in all frames of reference, it's going to look to you like these two events, namely the light going off and the detector detecting the light, are going to be separated by a certain amount of time, right? This physical distance should clue you in on exactly how far these are apart in time, because the speed of light is always this 3 × 10⁸ meters per second, right? And so presuming that this is only like, a couple meters up at the most, this is going to go very, very quickly, right? Something like 1 times 10 to the minus 8 seconds, a very, very small time window. But the moral of the story is that the distance that the light appears to travel will tell you how far apart these two events are in time, right? Now, let's drop another scenario. Let's say instead of being this person here, you are the observer here watching the train go by. Okay, well, so the train is going to start here, let's say. And this train is moving very fast, some kind of relativistic velocity, very, very quickly, right? Some significant portion of the speed of light. It's going to start here. Here's our friend the mirror. Here's the detector. Here's the filaments. This is our light bulb, right? And here, the light is getting generated. And then some later time, the light is going to hit the mirror and bounce off. And then some even later time, erase this now. Here's our light bulb, right? Here's our detector. Here's our mirror. Here's our wall. Now, because you're this observer and you're watching the train go by, it's going to look to you like the light starts here, right? It's going to go all the way up to this mirror and then all the way down to the detector here. And so in this observer's frame of reference, because this observer is not on the train, it's going to look like the light is going to take a much longer path than just the straight up and down. And so for this observer, because it looks like the light goes a much longer path, the lighting up of the light bulb and the detector detecting the light, these two events are much farther apart in time. This is called time dilation. And it is one of the effects that is brought into reality by this branch of physics that we call relativity. In this case, this is what we call special relativity. In any case, it's crazy, right? It's interesting. But I promise you it is the truth. Now, there's a formula that goes along with the time in a frame of reference, what we call the proper time. And the time in a frame of reference that is moving relative to the inertial frame. So if we're talking about the time in this observer's frame, where it just goes up and down, right? And this entire frame of reference is moving with the phenomena that cause the events. This is called your proper time, which we usually just call this T naught, actually. Proper time. There is, of course, a formula for figuring out the time associated with this path, observed time, right, T. And that goes something like this. So T is equal to gamma T naught, where gamma is this funny thing. It's 1 over the square root of 1 minus v squared over c squared, where v is the velocity of the train. Now this is drawn a little bit exaggerated, not to scale, because for the geometry of this situation to be true, this horizontal piece could not be greater than the vertical piece, right? Because that means the train would be moving faster than the speed of light, which cannot happen. But if we wanted to figure out, say, the difference in between this path length, right, which is basically just straight up and down, right, that's just the speed of light. If we take velocity is equal to distance times time, or excuse me, velocity is distance over time, and we wanted to figure out the time associated for some object moving at a certain velocity, moving at a particular distance, we get time. I'm sorry. Let's look for the distance instead. Distance then is time times velocity, right? Now, if we wanted to figure out this distance, right, we take the proper time multiplied by the velocity, or c, right? And the horizontal piece, well, that's going to be the total time, right, this time, times the velocity of the train. And so then we're going to end up with, essentially, a Pythagorean situation, right? This up and down branch is the speed of light times the proper time. This horizontal branch is the velocity of the train times this, whatever you call it, inflated time, right? And so the actual time gives us the speed of light times time, right? Of course, for this to work, we have to square everything, and then we have a true Pythagorean relation. So, if you want to write it out this way, c squared t squared is equal to v squared t squared plus c squared t naught squared. I know this is starting to look like a bunch of crazy mumbo jumbo, but let's just see how far this rabbit hole goes, shall we? Okay, what we're going to do now is we're going to multiply through by 1 over c squared, okay, this line. So we're going to multiply through by 1 over c squared, and actually, you know what? Let's subtract this to the other side first. C squared t squared minus v squared t squared is equal to c squared t naught squared. Okay, now we're going to multiply through by 1 over c squared. So this is going to be t squared minus, now we're going to have v squared over c squared times t squared. Or t squared times 1 minus all of that is equal to t naught squared. Okay, now we're going to take this and divide it under here. So we're going to end up with t squared is equal to t naught squared over 1 minus v squared over c squared times t squared. No, that's not right. Sorry. I made a boo-boo here. So there's, by making this 1 minus, we took the t squared out. Sorry, forgot the factor. Lucky. Hello, Katie. Where was I? I hope Lucky didn't ruin the focus on the camera. In any case, let's see. Oh, it looks pretty clear. So, where were we? We've got an expression for t squared. If we just take the square root of everything, we're going to end up with t is equal to t naught over, and the square root of all this, square root of 1 minus v squared, sorry, the factor term, over c squared. Or t is equal to this thing that we called gamma times t naught. Whew, complex, right? In any case, we have a nice relationship now in between what we call the proper time and the actual observed time, depending on the frame of reference, as long as we know this thing, v, the velocity of the object or the frame of reference relative to the inertial frame where these events are taking place. So how do we interpret this? Well, let's take a few limiting cases. Let's say you've got a really, really slow velocity, right? Something that's really small, something that's not really a significant portion of the speed of light. Basically, you get 1 minus 0, and then your time reduces to the proper time. No surprise there, right? Now, let's say we've got a really, really high velocity, like half the speed of light or something, right? Then time is much longer in the light clock's frame of reference. We get 1/2 squared over 1 squared. This is like a quarter, right? 1 minus a quarter is 3/4. 3/4 square root is a much larger... Okay, why did you do that? It's a much larger fraction of the speed of light. And so we can immediately see that if you have something like half the speed of light, this time is going to be inflated a lot compared to the proper time. Also, let's say v is the speed of light. Okay, so you get 1 minus 1, that's 0. Anything divided by 0 is undefined. And what happens is your time function blows up. And if you can actually manage to move at the speed of light, time ceases to progress in your frame of reference. That's right, time stops if you move at the speed of light. Now, don't go thinking that you can become immortal by doing so. Time will just sort of seem to cease to pass in your frame of reference. And so, let's say you've got a spaceship that moves at the speed of light. You're just going to go faster and faster and faster until all of a sudden it looks like time has stopped. Sorry, my cat is walking on the cable here. And basically, you're not going to know that any time has passed until you slow the vehicle down, you reduce the throttle and the velocity of the ship, and then you've gone a huge distance without feeling like any time has passed for you. So you will not live forever in really any kind of conventional sense. The amount of time that has to pass in your frame of reference is still however long you're going to live. In any case, the example that the book uses is this thing called the twins. Now, the observers don't have to be twins, but, I mean, I guess they could be. And this is also supposed to help to provide an example for proper time and observed time, right, depending on the frame of reference. Lucky had to push it again, sorry. In any case, let's say that we start here with the Earth, and one twin is standing here on the Earth, and the other one is on a spaceship that's moving at some relativistic velocity, right? Really, really fast. Now, the other twin is sitting here on Earth watching with a telescope to look for a light signal. And this ship is going to send out a light pulse every 6 minutes. Now, if the spaceship was stationary, not moving, then every 6 minutes one of these light pulses would get to the Earth, right? If the ship moves toward the Earth, let's say this way instead. Let's say the ship is moving toward the Earth, right, at some relativistic velocity. Now, like I said, if the ship was stationary, one of these pulses would get to the Earth every 6 minutes. But if this object moves towards the Earth at maximum velocity, then the twin on the Earth will see one every 3 minutes, because the distance in between these is going to be getting less and less, right? But if the ship is moving away from the Earth, then these pulses are going to appear farther and farther apart. And in this case, we'd see one every 12 minutes, every 3 minutes moving toward, and every 6 minutes if it's just stationary, right? Not moving toward or away from the Earth. Now let's say that the space pilot is gone for 2 hours in her frame of reference. And she fires a pulse of light every 6 minutes for a total of 20 flashes, right? The twin on the Earth is going to see the first 10 flashes 12 minutes apart as the first twin is moving away, and then as we're going back, the next 10 flashes will be 3 minutes apart. Okay? Now, the first 10 flashes, 12 minutes apart, that's 120 minutes, right? And then 10 more at 3, that's another 30 minutes. That in total, that's 2.5 hours, right? That's 150 minutes. Now, the total time in the ship's frame of reference, it's going to be 6 minutes apart 20 times. 6 times 20 is 120. So the proper time, T0, for the lights being sent out from the ship in the ship's frame of reference is only 2 hours. Crazy, right? Now, if the Earth is sending the light pulse, believe it or not, it's actually still the same, because now the twin on the Earth is going to fire a pulse of light every 6 minutes for 2.5 hours, for a total of 25 pulses. And the twin on the ship is going to see the first, sees them 3 minutes apart for if the twin is going towards the Earth, and then 12 minutes apart if this person is moving away from the Earth, right? However, in the ship's frame of reference, only 120 minutes goes by, because you're still talking about 10 pulses at 12 minutes apiece, and then 10 pulses at 3 minutes apiece. Crazy, right? When the ship is traveling away for 60 minutes, of course, it only encounters 5 light pulses. And when returning, it encounters a burst every 3 minutes for a total of 25, or for a total of 20 bursts of light. And again, 20 times 3 is 60, and 12 times 5 is 60, right? And so, again, we get 120 in total for the proper time. Crazy, right? Long story short, it's always the object that's moving that moves slower in time, right? If you're inertial, if you're not moving relative to something else that's moving faster, then your time is going to be slower, right? Object is going, or excuse me, the frame of reference, the time in a frame of reference of an object that's moving faster is going to experience a slower time. Now normally, if you wanted to find out how fast two objects were moving relative to each other, you just kind of add them up, right? If you've got a car moving to the right with 100 miles an hour and a car moving to the left at 100 miles an hour, when they collide, that's a 200 mile an hour collision, right? However, for velocities close to the speed of light, they don't quite add so simply and easily. We have to use this craziness, where the total velocity of two objects approaching each other or moving away from each other, c squared, can be solved this way. This is for relativistic velocities. Now the book goes on for some length to talk about how space travel is not possible with conventional means, saying things like finding enough fuel to accelerate at 99% of the speed of light is not feasible, and this unfortunately right now is true, right? If you wanted to try to travel to some distant corner of the universe, trying to do it with our current technology is probably not the best of ideas. As a matter of fact, even trying to get to Mars is crazy, and we're not going to do it very quickly. But trying to move to some distant part of the universe, even one as far as the nearest neighbor star to us, Proxima Centauri, which is only 4.3 light years from us, would take something like 100,000 years with our current technology. Crazy talk. In any case, the author goes a very, very long, roundabout way in describing what we call look-back time in astronomy. That is, if you recall, light is the ultimate speed limit in the universe. Nothing moves faster than the speed of light. So, since light is invariant in all frames of reference, the speed of light that is, if you look at some object like the Andromeda Galaxy, which is 2.5 million light years away from us, then the light that's getting to us now from the Andromeda Galaxy had to have been emitted 2.5 million years ago. Thus, we're not actually seeing the Andromeda Galaxy as it is now, but as it was about 2.5 million years ago. The author, however, does not go into any detail about how we're hoping to use our knowledge of relativity to try to bend the fabric of space-time in order to overcome the universe's ultimate speed limit, what they call warp drive, or the folding of space and time to move through the space-time that makes up the universe without actually having to achieve a velocity. And that's how we're hopefully going to try to beat this universal speed limit. One of these days, if we can, not die of destroying our own environment or COVID or whatever have you. In any case, the speed invariance of light also gives rise to a phenomenon called length contraction. Simply put, if an object travels at relativistic speed, it appears shorter in the direction it travels. Let's imagine for a second that you're going to take a meter stick and you're going to throw it with some relativistic speed, really, really fast, right? Some kind of relativistic velocity. Now, if you're here, this is your eye, and you're observing it, the light is going to travel towards your eye, right? The light from the back is going to travel towards your eye, and the light from the front is going to travel towards your eye. Now, doubtlessly, the light from the back is going to get to your eye first, right? At some later time, the light from the back is going to move towards your eye, the light from the front from there is going to get moved towards your eye, blah, blah, blah. And eventually, at some even later time, because this thing is moving really, really fast compared to the speed of light, right? It's some significant portion, and it just has some finite length. What's going to happen is the front from some earlier point in time is going to get to your eye about the same time that the back, the light from the back is going to get to your eye from some later point in time, and it's going to look like this meter stick is much smaller, right? That's what you're actually going to see. The front from some earlier point in time and the back from some later point in time. We call this length contraction. And suffice to say that length contraction only happens in the direction that this object is moving. The faster the object travels, the smaller that it appears in that direction. And we say the observed length is equal to gamma times the inertial or original length. According to Sir Isaac Newton, the change in momentum for a particle approaching the speed of light is infinite. However, the speed limit is not infinity. You can change the momentum of a particle indefinitely, but not its velocity. Einstein correctly showed that the momentum of a body moving at relativistic speed is gamma mv. This is proven by moving faster and faster accelerated electrons through a magnetic field, showing that they were deflected less when the electrons had more momentum. That was our mass spectrometer. Now, stationary matter has a certain amount of rest mass energy, or a certain amount of energy that would be released if all the matter were converted into energy. And the relationship in between this energy and the mass is this familiar relation, E equals mc squared. That means if you convert even a small amount of matter into energy, this c squared factor, because the speed of light is a really big number, it means if you take a small amount of mass and convert it into energy, you get a whole lot of energy. This is true if you're talking about burning coal or using nuclear fuel or whatever, it doesn't matter. And that's why you can use the uranium fuel, right? A chunk of uranium about the size of a lemon or so to power a nuclear submarine for about 2 years. Now the reason that you can use a tiny little lemon-sized piece of uranium to run a submarine for 2 years, but you need 1,000 tons of coal to run a power plant every day, is that nuclear fission fuel actually loses some of its mass as it decays, something like 1 part in 1,000. But fossil fuels use more like 1 part in 1,000,000,000 when they get burned into ash and soot and so forth. And so more matter, more actual mass, gets converted to energy when something undergoes nuclear fission. In any case, I hope you've enjoyed your lecture. We've got one more left, chapter 36, and that will be our last lecture for the semester.